All right, everyone. So today is going to be a pretty straightforward day. In fact, I don't think I'm going to hold you guys as long as I did last time because on today we're not going to be doing any mathematics or any mathematical problems. Today is just largely focused on concepts. We're still talking about waves, but we're going to get into the characteristics of wave behavior. So um, let me go ahead and share my screen. Kind of just go over briefly what is in Schoology. Okay. Like I said, today is going to be a pretty straightforward day. So we're in the first period. Click on materials. It's 6 weeks. Today is March 24th, and it is a Wednesday. Okay, so we're in the middle of the week. Okay. Now, on today, we're actually talking about wave actions and wave characteristics. Basically, what you need to do, you guys need to just listen to this lecture, understand the definitions and the concepts, and you will be ready to do this assignment. Okay, so there's not going to be any math involved today, just concepts. Okay, today I don't think it's going to be that difficult if you pay attention. I think you should be more than ready to do the assignment on your own. Okay, so um, let's begin by reviewing what we talked about last time. So, as you guys know, a wave is a process that repeats itself over and over again. It's basically a topic under harmonic motion. So now there are several ways you can create waves. You can create water waves, light waves, sound waves. You can create waves in a slinky, such as what we see here. So these two guys, they're holding a very small but very long slinky, and I want you guys to watch this man on the left here. So this man on the left, as he's holding this slinky, um, he's going to basically shake his hand up and down, right? So as he flicks his hand or flicks his wrist up and down, he's going to send pulses of energy traveling from this point in the slinky all the way to that point. Okay. So and as he do that, notice how he creates several transverse waves. Okay. So he's creating transverse waves in the slinky. Okay. So we have a pretty good idea about how to make waves. Basically, you just, in this case, you send pulses of energy several times through this medium here or through this slinky, and it creates waves. Now, what I want to focus on today, I want to focus on various characteristics of these waves. In other words, um, wave action definitions. So, for today, there are four major definitions you guys need to know. Here, I'm just going to give a simple definition at first, and then I'm going to go into more detail with each. So you guys need to understand four terms: absorption, reflection, refraction, and diffraction. So absorption just refers to when a wave is dampened inside of a soft boundary. Reflection, a wave bouncing off a hard boundary. Refraction, a wave bending inside transparent objects. And diffraction, when a wave bends around a corner. Okay, so these are just very simplified definitions, but in a moment I'm going to give you guys more detailed definitions of wave actions. And of course, I'm going to give you guys several examples as we go throughout these terms one by one by one. Okay, so like I said, we're dealing with reflection, refraction, absorption, and diffraction. That is the topic of today. Just going through these characteristics again. There's no math involved. We're just going to just explain the concepts. Okay. So let's start with explaining reflection in more detail. So look at the definition on the screen here. Go back here. So reflection involves a change in direction of waves when they bounce off of a barrier. So everybody can see that? That's the key word, bounce off of a barrier. And of course, guys, you're going to have better reflection when your barrier is hard. So consider this example here. Okay. Imagine here, just imagine here that I have a long slinky here attached to a wall, a hard wall. And just like in the previous video, imagine that there's a man here off to the side and he's holding this slinky here. So he's kind of holding it. And he's going to flick his wrist one time. He's going to send a pulse of energy traveling through the slinky. Okay. So, guys, in just a moment, I want you guys to notice something. As the pulse of energy travels, I want you guys to notice what happens when it encounters this wall here. So in just a moment, I'm going to show you guys that. So watch this. Okay. So once in a pulse. Okay. All right. Did you guys see that? So the pulse started off over here and traveled this way. And when it bounced off the wall here, it came back in the opposite direction. That is an example of reflection. And notice why we called it reflection, because notice the returning pulse was a mirror image of the incoming pulse. And I want you guys to see that again. So we're going to give a quick flick. Notice what happens to the pulse. Notice, did y'all see that? So the pulse was traveling this way to the right, and then it bounced back toward the left. So that is an example of example of reflection. Basically, you have pulses of energy bouncing off of some sort of hard barrier. Okay. Here's another example of reflection that you guys may be more familiar with, and that is reflection of sound waves. So, have any of you guys ever been standing outside? And I'm pretty sure you guys have. You've been standing outside, and let's just say there's a tall building in front of you, or a really large wall. Or maybe you're outside and you're near a canyon or something like that. And imagine that you're standing outside and you have these hard, tall objects in front of you, and imagine that you yell "Echo!" and you hear "Echo! Echo!" So what's going on there, guys? That is clearly an example of reflection. Right, when you yell echo, guys, you are creating sound waves in the atmosphere, right? Because that's what sound is. Sound is nothing more but a pressure wave in the atmosphere. Basically, you're causing the particles around you to move and vibrate. So, as you yell echo, the reason why you're able to hear your response sometime later is because basically the sound coming from your mouth travels in this direction, bounces off some sort of hard barrier, and then it comes back to your mouth or to your ear as represented by the dotted line. And so you're able to hear your own echo. Okay, so these are real world examples of reflection, basically just, waves bouncing off of a barrier. Okay, so hopefully that makes sense. Okay. Let's move on now to talking about absorption. Okay, now, so here's the detailed definition of absorption. Absorption is when a wave comes in contact with the medium and causes the medium's molecules to vibrate and move. This vibration absorbs or takes some of the energy away from the wave, and less of the energy is reflected. Okay. Now, here is a real world example of absorption. Guys, imagine right here that you're outside and you're looking at a black pavement. Okay. You're looking at the black pavement. Guys, as you're looking at this pavement and you wonder to yourself, why does this pavement appears black even though there's sunlight outside? Well, the reason why is because of absorption. Basically, what's going on as light waves come in from the sun and they strike this pavement, most, if not all, of the light waves are absorbed by the pavement. In other words, they're sucked into the material. And they cause those molecules to vibrate and heat up. And so eventually the pavement will feel hotter. Okay, so it feels hotter and it looks black because of pavement. excuse me, because of absorption in the pavement. Okay, because guys, think about what blackness is. Blackness is the absence of light, right? If you were to see something that is white, obviously all the light waves are being reflected toward your eyes. But if something is black, there's pretty much no light waves being reflected to your eyes, and that's because the pavement absorbs the light waves. Okay, the pavement absorbs the light waves. Okay, so that now in this particular example right here, not obviously not every single wave is absorbed, but you know, most of the waves, you know, if nearly all of the waves are well, most of the waves are absorbed because it appears black. Um, Another example of absorption. Imagine that you're in the middle of a padded room. So the, you know, the walls are not hard and rigid because you're in a padded room. And if you yell echo, you notice you may not hear yourself that well. It's because basically the soft walls are doing a very good job at absorbing the material. So it turns out softer objects are better at absorbing waves. Um, um, Excuse me, I'm confusing myself. Softer objects are better at absorbing waves in the material than hard objects, right? Because hard objects want to reflect the waves. Softer objects tend to want to absorb the waves. Now, some reflection can take place in softer objects, but you get more absorption in softer objects. Okay, so just something to keep in mind. Okay, now let's move on to talking about refraction. Okay, so in physics, refraction refers to the change in direction of a wave passing from one medium to another, or from a gradual change in the medium. Okay, this is best explained by an example. Okay, have anybody in here ever looked at a glass of water with a straw inside? And if you notice here, when you look at this glass of water with this straw, notice that this straw appears to be broken at the surface. It appears to be broken at the surface. The reason why it appears to be broken at the surface is because of refraction. Okay, so so basically, guys, what's going on here? As light waves come in here, and as they strike this water here, light waves basically they're transitioning from air to water. Okay, so they're transitioning from air to water. And so as they transition from air to water, they change their speed. And so by changing their speed, that causes the light waves to bend. And that bending of the light waves as it travels from one medium to the next is what causes this effect here where the straw appears uneven. It appears broken because we have refraction that is taking place. Okay, so everybody got that? So refraction is the bending of waves as a result of a wave changing mediums. In this case, we're changing from air to water. Okay. Now, I want to conclude the day talking about diffraction. Okay. Now, like refraction, diffraction also involves bending of waves, but in this case right here, you get diffraction whenever there's a bending of wave around corners of an obstacle or through a slit or an aperture. So let me read this in its fullness. Diffraction refers to various phenomena that occur when a wave encounters an obstacle or a slit. It is defined as the bending of waves around the corner of an obstacle or through an aperture. Okay. Guys, to best explain diffraction, I have a quick video here by Mr. Anderson from Bozeman Science, and I just want to show you guys this quick video clip because Mr. Anderson does a really good job of explaining diffraction. So I'm just going to show that to you guys now.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 110. It's on wave diffraction, which is the bending of waves as they move around an obstacle or through an opening. And so you can imagine these are water waves here moving from left to right, and this is an obstacle put in their path. And so as these ones on the top, they just keep going and going and going, but these ones right here are being diffracted. They're slightly bending around that obstacle. If we look down here, as they move through an opening, diffraction occurs as well. We're seeing that diffraction of these waves on this side. But there's not a lot of diffraction going on. And the reason why is the obstacle is much bigger than the wavelength. What happens if we make that obstacle or that opening the size of the wavelength or smaller? We get true diffraction. So what's happening is we're bending and we get these concentric circles that are moving out from there. Now, wave diffraction is going to occur if we have an opening for water waves like this, but all waves can be diffracted, even light. So if we put diffraction grating, small slits, we can actually diffract light and break it into its different constituent parts. And so wave diffraction occurs when we have either an obstacle or we have some kind of an opening. And as the waves hit the obstacle, they'll bend slightly around it. So an obstacle can diffract waves and also a slit. So as it moves through, we're going to see a slight amount of diffraction as well. It's bending around that opening. But what happens if we take that slit and we make it the size of lambda, the size of the wavelength? What you get is true diffraction that's going to look like that. So what's an example of this? Let's say that you are here and somebody is talking in another room. Can you hear them talking? Yeah, and that's because the sound waves are relatively large. As they move through the door, they're going to be diffracted, so you can hear what they're saying. It might not be super loud, but you can still hear it. Now, can you see them around the corner if you're in a different room? No. Even though light can be diffracted, look at our opening. Our opening is so big compared to the wavelength of the light that it's not bending around that corner. Good way to see wave diffraction is to use a ripple tank. And so what you do is put a table that has water in it. You then have a motor that just goes up and down. And as it goes up and down, this board oscillates and that creates waves that move out. You can shine light through it and then we could take a picture on the bottom. And so this is what it would look like where you have these waves that are being created and then you could see this gap. So they're moving right through this gap right here and so you see diffraction on the other side. Now, the size of that gap is important. If you've got a gap that's really, really large in relation to the wavelength, small diffraction, but if we decrease it to around the size of the wavelength, then we're going to get true diffraction. Here's a little PHET simulation of that. So we're generating some waves on the left side, water waves, and we're seeing diffraction over here. You can see it bend around. But watch what happens as we make that smaller and smaller and smaller. Look at that. We're getting more and more diffraction around that obstacle. Same thing with an opening. We don't have much diffraction on the edges of that, but watch what happens as we decrease the size and then we get it close to a wavelength. Then we're starting to get true diffraction. So this occurs for water waves. This could be a speaker on the left that's generating sound waves. You can see we've got diffraction of those sound waves as they move through that opening. And we'd also find that we're going to have wave diffraction if we're looking at light. So we're generating light. If we can make that opening so it's around the size of the wavelength of the light, again, with light it's going to have to be really, really small, then we can get diffraction. We could even see it in the wild. So we've got right here waves coming in on the ocean. There's a little opening right here, and you can see that diffraction as it moves through that little gap in the water. And so did you learn to make claims about the diffraction pattern? That's the pattern created as we move through a small opening. Again, we want to match the wavelength, and I hope that was helpful.
All right, guys, so that was diffraction. Okay. And by the way, just to be clear, the difference between the main difference between diffraction and refraction. So both of those processes involve bending of waves, but understand diffraction occurs when you have bending of waves around some sort of barrier or obstacle. In the case of refraction, you have bending of waves because you have a wave transitioning from one medium to the next. In the case of going from air to water, okay. So there is transferring from one material to the next. So that's refraction, but diffraction deals with the bending of waves whenever you're encountering obstacles or barriers or slits or openings. So just so you guys understand the difference. All right, so okay, you know what? Last thing that I want to do with you guys today before I let you guys go. I just want to just go over just a few of the questions from the assignment, just so you guys can have an idea of what I'm looking for. Because like I said, we're just understanding concepts here. So this assignment is already open. You guys can click on it and get started with it. Um, there are about 12 questions. I'm just going to go over this 3 of these with you all. Okay, I'm just going to go over 3 of these with you guys. So look at this question right here. It says carpet can keep a room quiet by what? So guys, carpet is obviously something soft. So if it keeps a room quiet, obviously there must be absorption of waves from the carpet, right? So like if you're yelling, and yet you don't hear that much in return, it's because the carpet is a soft object that is absorbing a lot of the waves, and very little waves are being reflected back. So it's because of absorption. Absorption is basically sucking in of those waves. Okay. Let's look at some more. Okay, eyeglasses magnify objects by what? Okay, so guys, if I have eyeglasses, and light waves are coming toward my eyes, obviously those light waves experience a transition they experience a transition of mediums, because they're going from air to glass. So therefore eyeglasses are magnifying objects by bending those light waves. So obviously that is from refraction, okay, because we're transitioning mediums. Okay. Tile or marble makes for a loud room by what? Okay, so guys, tile is a very hard object. So if you're in a room with a lot of tile and you yell echo, you might hear yourself because of reflection, right? The sound waves are loud because of reflection. Okay, remember, because you get reflection whenever something bounces off of a hard object. Okay, so I'm just going to do those 3 with you guys. The remainder I want you guys to finish on your own. I just wanted to give you guys an idea of how to think through these questions. Okay, does anybody have any questions, any final questions for me? Okay, this video clip will be on this video session will be on YouTube. If you guys don't have any final questions for me, you guys are free to go. Please fill out the attendance form if you have not done so. Okay. All right, guys, I'm going to keep the Zoom call open up until 9 o'clock in case you guys need help. Bye, guys.